Hello everyone, my name is Zhao Ying and I'm from the University of Aizu. Uh, I'm excited to present our paper Balancing Exploration and Exploitation in Maximum Diffusion Reinforcement Learning using Evolutionary Computation algorithm. Let's start with the core motivation for our work. As many of you know, one of the most fundamental challenges in reinforcement learning is the exploration and exploitation dilemma. How do we decide whether to try something new to find a better reward, or to stick with the best strategy we have found so far? A promising recent framework called Maximum Diffusion Reinforcement Learning, or MaxDiff RL, addresses some key issues in RL by reducing temporal correlation in data. However, this introduces a new bottleneck. The performance of MaxDiff RL is highly sensitive to a single fixed temperature parameter, which we call alpha. As you can see from the diagram, alpha is the fulcrum that balances exploration and exploitation. This raises a crucial question. How do we assess the optimal value for alpha? And to understand the problem better, let's briefly look at how MaxDiffRL works. As shown in Figure 2, MaxDiffRL is a model-based approach. Its primary goal is to maximize trajectory entropy, which helps to uh, de decorrelate the data in age, an agent collects. The key idea is to plan paths that optimize for both the expected reward and path entropy. This trade-off is mathematically captured by this modified reward function. And in this equation, parameter alpha directly control how much weight is given to exploration versus exploitation. The problem is that in the original framework, this crucial parameter must be attuned manually. So, why is a fixed manually tuned alpha such a problem? First, the optimal alpha is task dependent. Different environments require different levels of exploration. A value that works for one task may fail completely on another. A second is stage dependent. An agent's need for exploration changes throughout the training process. Typically, more exploration is needed at the beginning, and more exploitation is needed towards the end. A fixed alpha cannot adapt to this. And finally, find a good alpha is insufficient to twin. Manual twinning is difficult, it's time consuming, and the result is often suboptimal. This is the core problem we set out to solve. This brings us to our proposal, a dynamic balance mechanism. Our solution is to use an evolutionary algorithm, or EA, to dynamically tune the temperature parameter alpha during the training process. Why did we choose an EA? For three main reasons. First is adaptive. It can continuously adjust alpha based on the agent's actual performance, measured by its reward. Second, it's efficient. It completely automates the training process, avoiding uh, tedious manual work. And third is robust. The population-based nature of EAs improves the search for a good solution and enhances stability. So how does our EA implementation work? It follows a simple uh, iterative three-step process. First, we maintain a population of candidate alpha values. And second, in the mutation step, we generate a new population by taking the best performing alpha from the previous generation, which we call the elite, and adding some random noise to it. Finally, in the selection step, we evaluate all these new candidates by measuring the agent's performance. The candidate that yields the highest cumulative reward becomes the new elite for the next cycle. This loop continues throughout the training. To make our method more effective, we incorporated two key details. On the left, um, we use a staged adaptation. We divided the entire training process into three stages. The mutation strength sigma is varied across this stage. It's set higher at the beginning to encourage bolder exploration of alpha values, and lower at the end to fine-tune the parameter. And to ensure training stability, we use a clipping strategy uh, inspired by PPO. This prevents overly aggressive updates the alpha by constraining the new value to be within a small range of the previous value. Now, let's move on to our experiment. We evaluated our method on two continuous control tasks from the musical physics engine, swimmer and half cheetah. We compared three methods. Our proposed method with a dynamic alpha, the original maxdiff IL with its default alpha, and the original maxdiff IL with a randomly initialized alpha. And our evaluation was based on three key metrics: the cumulative reward, the stability of the training process, and the statistical significance of the result. Here are our main performance results. The solid lines represent the average cumulative reward, and the shaded area are the 95% confidence intervals. On the left, for the half-cheetah task, our method performs comparably to the well-trained default, and it's significantly better than using a random parameter. However, the result on the right for swimmer task are more striking. Here, our method significantly outperforms both baselines. It converges faster and achieves a much higher final reward. The key takeaway is that our dynamic approach shows clear and significant advantages in tasks that demand a greater degree of exploration. To further validate these findings, we analyzed the stability and the statistical significance. So looking at the table, if we focus on the swimmer task, we can see two things. First, in the table 1, our method not only have a higher mean reward, but also much lower relative standard deviation, indicating a more stable and reliable performance. Second, in the table 2, the main Whitney U-test confirms that the improvement is statistically significant with a p-value of 0.008. This confirms that our method provides a genuine performance gain. So, what is the alpha parameter actually doing during training? This graph shows its evolution over time. For a half cheetah on the left, alpha remains relatively low. This tells us that the task itself does not require a high degree of exploration. In contrast, for swimmer on the right, alpha quickly rises stays high. This shows that the agent discovered that continuous high intensity exploration is necessary to succeed in this task. And the key insight here is that the fluctuation of alpha is a feature, not a bug. The algorithm is not trying to converge to a single point. It is actively adapting to the real-time needs of agents. Let's briefly discuss these results. So why does our method work so well, especially on the swimmer task? The primary reason is dynamic adaptation. The EA successfully creates a feedback loop that adapts the exploration and the exploitation trade-off in response to the environment. It also makes the process much more efficient by automating the training. And why was the improvement on half cheetah not as significant? We believe there are two potential reasons. The performance bottleneck for that specific task may lie elsewhere, not in exploration. It's also possible that the default baseline parameter was already very close to optimal for that task. In conclusion, we have proposed an evolutionary algorithm-based method to dynamically solve the exploitation dilemma in maximum diffusion reinforcement learning. Our approach adaptively tunes the temperature parameter alpha to meet the changing needs of the task and the training stage. And our experiment demonstrates that this method leads to faster convergence and higher rewards, especially in tasks that require significant exploration. Of course, our work has limitations and opens up avenues for future research. Our current fitness evaluation is based on short-term rewards, which may not always capture the quality of a long-term strategy. Also, the EA does introduce some computational overhead. For future work, we plan to explore more robust long-term fitness evaluation metrics. We are also interested in jointly optimizing multiple hyperparameters, not just alpha. And finally, we plan to benchmark our approach against the other dynamic training method. Uh, okay, this concludes my presentation. Thank you very much